This is the first video on section 4.1, vector valued functions. Now, what is a vector valued function? In Calc 1, we talk about the definition of a function. It's a rule that assigns something from a set, call it x, into something in another set, call it y. And sometimes we define this function very abstractly, and then in Calc 1, the set x is always a subset of the real line, the set y is always a subset of the real line. So we get an idea that a function is something that takes a number and gives it another number. That's one type of function, but it's not the only type of function, as we're going to learn in this course. Another type of function is called a vector valued function. What does a vector valued function do? It's a function from the reals, or actually some subset of the reals, into v sub n. And in this course, it's usually going to be v sub 2 or v sub 3. In other words, a vector valued function takes a number and assigns a vector. So let's look at an example of some vector valued functions and their graphs. So in the notes, you're going to notice that I use a bold-faced F here. It's similar for a vector notation, and that's because I want to distinguish the difference between what we normally consider as functions and our vector valued functions. So this function takes t and assigns it the vector whose first component is t to the fourth and whose second component is t squared. A lot of times when we graph these, especially in two-space, we want to sort of consider what an analogous real valued function might be. So in this case, let's compare this to the curve x equals y squared. Why? Because if I take this component and I square it, I have the first component. So we want to compare it to x equal to y squared. X equal to y squared is a parabola. But we're not interested in the entire parabola, because here x is always positive, y is always positive. So basically what we're doing is we're graphing these points they're the terminal points of this vector. And so that's what we've graphed here. And so the graph is basically half of this parabola. We drew these arrows in the direction of increasing t. When t is 0, we have the 0 vector, so that's a terminal point, is 0, 0. As t increases, our vector gets longer and longer and longer. And so this represents a terminal point of this vector. Here, for part B, f of t is t squared t cubed. Well, let's also consider y is x to the 3/2 power. If we take t squared to the 3/2 power, we have t cubed. Now, keep in mind as we do this, these are only guides. So here, this curve only gave us part of the function. Here, this curve isn't going to give us the whole function. If you look at this algebraically, it's only defined for a positive x. But here, our y's are allowed to be negative. And so, start by taking this curve and graphing it. So this part right here, this is a good starting point. Draw that. But as I said, that's incomplete because t is allowed to be negative. So we take this and reflect it below the x-axis and draw this part right here. Now, as t increases, what happens? Well, what happens when t is negative? When t is negative, y is negative. When t is positive, y is positive. And so as t increases, so negative comes up here to 0, we have the 0 vector, then t increases, now t is positive, so y is positive. So these arrows indicate the direction of the increasing t. We started with this. It was a good guideline, but it wasn't the entire story. Same thing with this. It's a good guideline, but it doesn't tell us everything we want to know. For part C, our vector valued function is t squared minus 2 and t. So what's a good guideline for a curve? It's x equal to y squared minus 2. Why? If y is t, then x is y squared minus 2. So we have this parabola. So we start by graphing this parabola. In this case, this parabola is a very good guideline because it does give us the whole curve. When t is negative, y is negative. When t is positive, y is positive. So these arrows indicate the direction of increasing t.